please.
Thank you. So I changed the title slightly from what was announced before. It's the same topic, but the different title reflects a change in emphasis. Because I decided what I was going to do, rather than explain technical details of one thing, was to try to give an overview. I won't give all the references that would be relevant, but one thing I'll say at the outset is that part of the inspiration was to get a new perspective on something that was done some years ago by Gukov, Waffa, and Schwartz. I'll explain a little bit more about that later on. So we start with n equals 4 Super-Yang-Mills theory in 4 dimensions. And one important thing in this theory is that it's got all kinds of BPS operators, that is, operators that have some supersymmetric properties. But the one which we'll care about is that you can take an arbitrary loop in space-time. Of course, you could make an ordinary Wilson loop operator, but it would be completely non-supersymmetric. But you can make a 1/16th BPS loop operator for an arbitrary loop in space-time. So you simply combine the gauge field A mu with 4 of the scalar fields, which I'll call phi mu. Mu runs from 1 to 4. And you define the ordinary Wilson loop operator, except that instead of A, you use A plus I phi. And then R is a representation of the gauge group. K is a loop over which you integrate, usually the gauge field, but here you integrate A plus I phi. So the Wilson loop operator, with this simple change, is invariant under 1 supersymmetry. So there's a quick way to see that it's 1/16th BPS. For each value of mu, making A plus I phi supersymmetric is true for half of the supersymmetries. But we have to do it for 4 values of mu. So we divide the supersymmetry by 2 to the 4th, or 16. And starting from 16 supersymmetries of n equals 4 Super-Yang-Mills, we're left with 1. So this operator is invariant under 1 supersymmetry. So I'll call this 1 supersymmetry Q. And to debase Q squared equals 0. Q squared could hardly be anything except 0, because if it's not 0, it would be a space-time translation. But an arbitrary loop isn't invariant under any translations. Since Q squared is 0, we can use this Q to define a topological field theory. In the topological field theory, we only permit ourselves to look at Q invariant operators, but we consider, you see, Q with anything is Q invariant because Q squared is 0. So we consider Q anti-commuted with anything to be trivial. We look at operators O modulo this relation. And that gives a sensible, more limited space of operators whose correlations which we can study. Because Q squared is 0, it's consistent to regard such expressions as trivial. And it gives a topological field theory because the stress tensor is trivial in this sense. The stress tensor is the response to a change in the metric of the space-time on which we do n equals 4 Super-Yang-Mills theory. So when we make the response to a change in the metric trivial, it means that whatever we compute will be independent of the metric. In other words, it will be a topological field theory. So starting from n equals 4 Super-Yang-Mills, you can construct a topological field theory that has observables that are Wilson loop operators for an arbitrary loop in space-time. So this actually is the same topological field theory that Kapustin and I used for geometric Langlands. Now, because of the facts I've said, the expectation value of the Wilson loop operator, WR of K, for any loop K and any representation R, is a topological invariant. But that's not interesting in the setup I've explained so far. If we were in 3 dimensions, topological invariants of loop operators would be interesting. That's because in 3 dimensions, a loop can be a hopelessly tangled mess like I've drawn there. So a topological invariant for a loop operator in 3 dimensions would be a knot invariant. And there are all kinds of knots. And having a way in quantum field theory to calculate an invariant of knots can be something interesting. But in 4 dimensions, there's nothing like that because You see, in 4 dimensions, we could move the strands past each other. In 3 dimensions, they get stuck, but if we're in 4 dimensions, we just move out of the way in the 4th dimension and move one strand around another, making everything trivial. So although we've got a 4-dimensional topological field theory with Wilson loop operators, that by itself doesn't lead to anything interesting. So that's why Kapustin and I didn't study these correlation functions. To get something interesting, we're going to study n equals 4 super Yang-Mills, not on R4, but on a half space. The half space will be, I'll call it R3 times R plus, where R plus is a half line. Let's say the half line where y, one of the coordinates, is non-negative. Now, obviously, since we're on a space with a boundary, we need a boundary condition at y equals 0. And the boundary condition we're going to use is the one that comes from the D3 NS5 system. Here's a very schematic picture of the D3 NS5 system. We have a lot of parallel D3 branes. They end on a single NS5 brane. So we're going to study the D3 brane gauge theory with the boundary condition that comes from the NS5 system. Now, this is a half BPS boundary condition. A single NS5 brane preserves half of the supersymmetry that the D3 branes would have by themselves. The D3 branes would have 16 supersymmetries, and the NS5 brane preserves 8 of them. One linear combination of these 8 supersymmetries is the supersymmetry that's preserved by the 1/16th BPS Wilson operator that I explained before. So, okay, this statement, the way I put it here, sounds non-generic. We have a subspace of 8 supersymmetries, and some random supersymmetry given by another condition I'm claiming is one of the 8. So this is, in a sense, a slightly lucky result, but if you took account of the rotation symmetries of the problem, it's not as absurdly unlikely as it might have just sounded. So we can have a topological field theory on a half space with Wilson loop operators for arbitrary loops. So it's true, but it's still not interesting. For the same reason as before, we can still untie any loops, any knots. Now, okay, actually, I made a slight misstatement. So this assertion here is true if the theta angle is 0. The D3 brane gauge theory has a theta angle. This boundary condition is more easily described if the gauge theory theta angle is 0. For instance, the boundary condition is just Neumann boundary condition for gauge fields, and every field obeys either Dirichlet or Neumann boundary conditions, or something simple at least. And then, in this if the theta angle is 0, what I told you is true, the supersymmetry of the 1/16th BPS Wilson operators is a linear combination of the supersymmetries allowed by the boundary condition. Okay. Somehow, I think we already did this slide. So, but just to repeat. So we do topological field theory on the half space. We've got arbitrary Wilson operators, but they don't do anything interesting. Now, we actually do get something interesting if we take the gauge theory theta angle to be non-zero. The D3 NS5 boundary condition is then trickier, and there's a simple reason to explain why it's trickier. We're turning on in bulk the QCD theta angle. So we're adding trace f wedge f to the Lagrangian. If we were on a closed form manifold, that would be the instanton number, a topological invariant. On a manifold with boundary, it's not a topological invariant. Trace f wedge f in bulk is like a Chern-Simons interaction on the boundary. So we're trying to supersymmetrize a Chern-Simons interaction in a situation where there are supposed to be 8 supersymmetries. But if you're familiar with 3-dimensional supersymmetric Chern-Simons theories, they're straightforward to construct up to 6 supersymmetries, but with more than that, they're tricky. The first example discovered, having been the Bagger-Lambert-Gustafson theory. So this is similar. It's a little bit tricky, but anyway, it exists because, after all, the D3 NS5 system with a theta angle exists, so the boundary condition has to exist. So the boundary, what's tricky about it is that although it still preserves 8 supersymmetries, which 8 depends on theta. That's what makes it a little bit tricky to write down this boundary condition. And in particular, the boundary condition no longer preserves the same supersymmetry as the 1/16th BPS Wilson operators, so they disappear. So the uninteresting supersymmetric Wilson operators go away, but we get something more interesting instead. Though a generic loop K does not support a Wilson operator that preserves a supersymmetry that's also preserved by the boundary conditions, a loop that's in the boundary actually does. So now we get this picture. This rectangle on the left is meant to be the boundary. This is the half-line direction. So if you like, this is R3 and this is the R plus direction. I'm not sure if the perspective is clear, but the knot here is meant to be in the boundary. And precisely if the knot is in the boundary, you can construct a supersymmetric Wilson operator for that knot that preserves a supersymmetry that's also preserved by the boundary condition. Now, this now becomes more interesting because now our loops are in 3 dimensions, so they can be knotted, as in the example I drew. So the expectation value of this Wilson loop operator will be different than the expectation value of an unknotted Wilson loop operator in the boundary. So finally, we're going to get something interesting. Okay. Maybe before going on, I'll say that, okay, first of all, once you suspect it's true, it's not a hard calculation to show that only in the boundary there's a supersymmetric Wilson operator. But I certainly won't do the computation for you. I will say, though, that if you have a Wilson operator in 3 dimensions, it preserves, it's 1/8 instead of 1/16th BPS. So it preserves 2 supercharges. And no matter what theta is, one linear combination of those 2 is also preserved by the boundary condition. So we've got potentially interesting Wilson loop operators, and we'd like to compute their expectation values. Now, since these operators and the whole construction are invariant under a supersymmetry Q that obeys Q squared equals 0, we can use a technique known as supersymmetric localization. The basic idea of supersymmetric localization is that the path integral over all fields can be replaced by an integral only over supersymmetric configurations. And there are a lot less supersymmetric configurations than there are all possible fields, so this reduces the path integral from the full path integral to something more manageable. This technique has all sorts of applications, some of which I think we'll be hearing about in later talks at this meeting. So my original title for this seminar was, I had in mind that the seminar would be devoted to just explaining this one thing, how to use this technique for this problem, but I changed course and decided it would be better to give you an overview. That's why I changed the title. Instead, I'll just say that if you do apply supersymmetric localization in this situation, what you learn is the following. You find out that the expectation value of one of these Wilson operators on the boundary of a 4-dimensional space can be computed in a purely 3-dimensional topological field theory, namely the purely bosonic Chern-Simons theory in 3 dimensions. So in other words, the answer, if you want to calculate these loop operators, the answer is that they're the same knot invariants that you can get from Chern-Simons theory in 3 dimensions. They're known as the Jones polynomial, that's for SU2 with the spin-half representation, and its generalizations. So localization reduces you to something smaller. In this case, the something smaller is still a quantum field theory, but it's a quantum field theory in 3 dimensions instead of 4. And it's got the virtue that it's completely soluble. So 3D Chern-Simons theory is completely soluble because of its relation to 2D conformal field theory. So all these invariants are explicitly calculable. So there's a hierarchy of relations between theories in different dimensions. Supersymmetric localization maps from 4 to 3, and then there's a much older story that maps from 3 to 2 and leads to these invariants being exactly soluble, calculable. Now, I wish there were time to review this today, but there really isn't. And likewise, as I've already said, I won't be able to explain in detail why localization of the D3-NS5 system gives a purely 3-dimensional description via Chern-Simons theory. Instead of explaining either of those things, we're going to discuss something else that's conceptually more straightforward. Once we get to 4 dimensions with n equals 4 super Yang-Mills, we can apply electric-magnetic duality. Electric-magnetic duality maps the D3 branes to D3 branes, but it turns the NS5 branes into D5 branes. So the D3-NS5 boundary condition becomes a D3-D5 boundary conditions, as I've schematically indicated with this picture. The same picture as before, except the D3 branes are now ending on a D5 brane instead of NS5. Electric-magnetic duality turns the Wilson operators into 't Hooft operators. So I've drawn now exactly the same picture as before, but it's supposed to tell you something different. The red knotted loop is now the support of an 't Hooft operator rather than a Wilson operator. Now, we still have a supersymmetric setup. So again, we can apply supersymmetric localization. But when we do it now, we get a more straightforward answer. So something that's true, when you do supersymmetric localization, the easiest thing that can happen to you is to localize on the solutions of some equations, which hopefully have a very limited set of solutions. And that's what happens to you here. The localization occurs on the solutions of a certain set of equations that are the conditions for Q invariants. I've written them here. They're equations for a gauge field. D is the covariant derivative. F is F mu nu, the Yang-Mills field strength. And remember, at the beginning of the lecture when we constructed our supersymmetric Wilson operators, we took 4 scalars and we combined them together into a one form on spacetime, enabling us to add them to A to make A plus I phi. So our equations are equations for the gauge field and phi, and in a compressed notation, they look like this. So these are equations that have been studied before. So they play the same role here. They're less familiar than the Yang-Mills instanton equations, but they play the same role, analogous role to the role that the instanton equations play in other problems. In n equals 1 super Yang-Mills, supersymmetric localization can restrict to solutions of the usual Yang-Mills instanton equations, and here you got these equations instead. So, well, I've written here something I just told you. When you apply supersymmetric localization, the easiest, conceptually the easiest type of answer is to localize on the set of solutions of some equations. And that's what we get for the D3-D5 system. Although for the D3-NS5 system, we got something more complicated, which was localization on a path integral of lower dimension. So localization here means that we literally just have to count the solutions of these equations, and then we can write down the path integral, the partition function, in terms of that count. Well, to be a little more precise, we have to take into account the Yang-Mills instanton number. We let an be the number of solutions of instanton number n. Then the partition function is the sum of an times q to the n. Where q is expressed in terms of a coupling parameter of the theory, in terms of the purely 3-dimensional description, q is written this way in terms of the 3-dimensional Chern-Simons coupling k. There's also a formula for q in terms of 4D n equals 4 parameters, although I won't write it. But in terms of purely 3-dimensional parameters, this is q. And then the partition function comes out to be given by a simple count of solutions for instanton number n. That's the prediction that comes out of electric-magnetic duality and supersymmetric localization. But since Chern-Simons partition function can also be directly computed by relating it to 2 dimensions, we can view this as a prediction for the numbers an, the number of solutions of those 4-dimensional equations. So apart from the exact solution of Chern-Simons theory, the prediction uses electric-magnetic duality and supersymmetric localization. So in a very recent paper, Davide Gaiotto and I verified this prediction by directly analyzing the equations and counting their solutions. So if you ask, a few people here have asked me what on earth we did in that long paper, this is the one-sentence answer. We tested this prediction of electric-magnetic duality. Now, there isn't time to explain what we did while also giving an overview, as I'm trying to do today, but one thing I can tell you is that a key fact is that although these equations are hard to understand in general, in the time-independent case, they become tractable. So it's hard to understand the 4-dimensional solutions of those equations, but if you drop the dependence on time, they reduce to 3-dimensional equations that you actually can understand. And then starting with the fact that we understood the 3-dimensional equations, and then reintroducing time in a sort of adiabatic approximation, we bootstrapped our way from 3 up to 4 dimensions. So, but I won't try to spell all that out. And in the process, we found out that these equations have a novel relation to other fun things, 2-dimensional conformal field theory and integrable spin systems. But we won't do that. Instead, there's, again, something much more straightforward to tell you about, which will lead to the main result of the paper I wrote just before it on 5 brains and nuts. So I'll also give the quick explanation of what on earth that paper was about. All we're going to do is we compactify one of the directions that we haven't talked about on a circle. In other words, the D3 brains were 4-dimensional, but if you add in the D5 brains, the picture I drew before was really 7-dimensional, leaving 3 dimensions of string theory that played no role in the discussion. So we take now one of them to be a circle. And then we apply T-duality. And the D3, D5 system becomes a D4, D6 system. So the D3 brain gauge theory becomes a D4 brain gauge theory. In other words, a 5-dimensional super Yang-Mills theory. And we can calculate the path integral using supersymmetric localization. And this just tells us to count solutions of some supersymmetric equations in 5 dimensions instead of 4 dimensions. But the count gives the same answer because, after all, T-duality is true. And the fact that the answer is the same isn't that deep. The reason it's not that deep is that T-duality is a weak coupling transformation. Where we got a deeper statement before, we used S-duality, which exchanged weak and strong coupling. So it contains information that's hard to see classically, but here we've just used T-duality. So we get an elementary relationship between equations in 4 and 5 dimensions. But we're going to do something else. In the D4 brain description, the knot is still represented by an 't Hooft operator, but the 't Hooft operator has grown an extra dimension. 't Hooft operators are defined by magnetic monopole singularities, which are of codimension 3. So in 4 dimensions, the 't Hooft operator is a line operator, but in 5 dimensions, it's supported on a surface, which is simply the knot times the 5th dimension. When we did T-duality, we grew a circle, and the 't Hooft operator grows that circle, so it's now supported on a knot times a circle. I won't use that in the rest of the lecture. I've just mentioned it because somebody might wonder what happened to the 't Hooft operator when we did T-duality. So what do we gain by introducing a 5th dimension? Nothing from what I've said so far. It was just a weak coupling transformation that mapped a theory in 4 dimensions to a theory in 5 dimensions. But the reason we can gain something is the following. First of all, since the D3 brains lived on a half space, R3 times R plus, the D4 brains live on the same thing times a circle. let's just focus on the fact that there's now a circle factor. So if we were doing the quantum path integral, we'd have a path integral on a circle. And a path integral on a circle gives a trace, or in the supersymmetric context, it gives a supertrace. So we could calculate the path integral by introducing what I'll call curly H, the space of physical states. But since we've restricted to Q invariant things, the physical states are the cohomology of the supercharged Q. So if H is the space of physical states in quantization of the D4 brane system on this spatial manifold, then the partition function is a trace, except it's a supersymmetric trace, which is otherwise known as an index. So instead of writing the trace Z as a count of solutions, as we did before, we can write it as a count of quantum states. A trace of Q to the P, where P is the instanton number, times minus 1 to the F. In other words, it's a supertrace. The minus 1 to the F is the super part. And in the previous description, we had Q to the N, where N was the instanton number. N was the eigenvalue of a conserved charge P. Well, in 4 dimensions, N is just a classical property of an orbit. But in 5 dimensions, instanton number integrated over an initial value surface is a conserved quantity, which I'm calling P. And then we get this expression for the partition function as a supertrace. So the partition function is an index. But you see, we always lose information when we take an index of anything, because some states might cancel out of the index. So whenever you calculate an index, it has less information than you had before you calculated the index. That's always true, but I've written in parentheses some more detailed reasons that in this problem we lose information by computing the index. One is that there was a conserved fermion number that's actually integer valued, but in the index we only remember the value of F mod 2. So we've forgotten the integer eigenvalue of F. And also, when we introduce a fifth dimension, we could have considered more general 't Hooft operators rather than the ones that have a supertrace interpretation. So we've several different ways we've lost information by taking an index. So there's a more powerful theory. Just study the space of physical states rather than the index. So Chern-Simons theory can be deduced by taking the index of a more powerful theory. The more powerful theory is known as Kovanov homology, which was developed about 10 years ago following ideas of Igor Frankl, and first interpreted physically by Gukov, Waffe, and Schwartz in 2004. So it's known that this more powerful theory contains significantly more information about knots. For instance, it's known that it gives a complete answer to the question of whether a given tangle can be untangled, which is not the case for Chern-Simons theory. So that would be interesting to discuss. But as physicists, there's something else we should worry about. So the D4 brane gauge theory isn't ultraviolet complete. So conceptually, it doesn't feel really satisfactory as the foundation for a description of this more powerful theory than Chern-Simons theory. However, it has a well-known ultraviolet completion in the M5 brane system, or more exactly, in the 6-dimensional superconformal field theory with 0-2 supersymmetry. The whole construction can be usefully expressed in 6-dimensional terms. The basic idea here is that what in the lecture so far has been the half-line R+, can be replaced by a copy of R2 with a cigar-like metric. So unfortunately, this is meant to be a cylinder of revolution, but my sketch is a little bit too rough to see the rotational symmetry. Topologically, the semi-infinite cigar is meant to go off to infinity. Topologically, it's R2, but we've picked a handy metric rather than the flat metric on R2. I've picked a metric which asymptotically is the product of a half-line and a circle. So I'll call this cigar D. It's a cylinder of revolution. We consider M5 branes on D times the rest of our space. What was the rest of our space? There was an R3 where the knots lived, and then we grew a time direction by T duality. So the M5 branes will be on the space where the knots are, the R3. Then there's the fourth dimension, the extra dimension that was introduced by T duality, and then we will replace the R plus direction by the cylinder of revolution. So we start with the M5 branes on a six-dimensional space, one of whose factors is the cylinder of revolution. Starting with M5 branes on D, if you reduce the M5 brane on the circle orbits, then the M5 branes become D4 branes, and D is replaced by D divided by U1, which is R plus. So this is completely familiar away from the endpoint. So away from the endpoint, we just have the product of a circle and something, and M5 branes on a circle give D4 branes. Now, you have to modify that a little bit near the endpoint, and the modification, after some standard arguments that I won't explain today, gives you the D4, D6 boundary condition, which we had a few minutes ago. So replacing D by D over U1, which is R plus, leads to the R plus factor that we had in the D3 NS5, D3 D5, and D4 D6 descriptions. Now, to a quantum field theorist, the M5 brane description is the most perfect one, but it's the farthest from Chern-Simons theory. To relate the M5 branes to Chern-Simons theory, you simply reverse all the steps that I explained in the lecture. You've reduced on the U1 orbits to replace D by R plus and M5 branes by D4 branes. Then you compactify in a circle to replace D4 branes by D3 branes. Well, compactify in a circle and make T duality. This step is irreversible. It loses information. There will be a sequence of steps. They're all dualities, except that here, when you compactify in a circle, you're taking a supertrace and you lose some information. That's where you replace a theory by its index, which is an irreversible step with information being lost. You apply S-duality to get to a D3 NS5 system. And finally, you use supersymmetric localization to get to a purely three-dimensional description in Chern-Simons theory. So there's a sequence of steps that lead from the M5 brane in 6 dimensions to the Chern-Simons theory in 3 dimensions. And then actually, the exact solution of Chern-Simons theory depends on its relation to 2 dimensions. Of the steps I've sketched here between the M5 brane and the 3-dimensional Chern-Simons, all steps are straightforward, standard S or T dualities or relations between M5 branes and D4 branes, except for the last one, which is conceptually straightforward, but still slightly tricky application of supersymmetric localization. Thank you.
And thank you for keeping the time. Question there?
You mentioned earlier that the top field K, after you do T-duality, you grow in S1.
Yes.
So is it possible if we include, say, a top loop and a Wilson loop and you grow in S1, it becomes a surface operator?
Well, first of all,
Ed, can you repeat
yes,
the question?
the question, I'll divide the question into 2. One question was, so 't Hooft loops are similar to D-branes. So under T-duality, they can grow directions. But Wilson operators can't grow directions under T-duality. And we can't really, we had Wilson operators before the, you could have asked me, what if we do T-duality before the S-duality? Of course you get something, but not similar to what I've said, because something funny happens to NS5 branes under T-duality. They turn into H monopoles with a different topology. So there isn't a good analog. There can't be an analog. Wilson operators are one-dimensional things that have no two-dimensional cousins. So they couldn't have grown an extra dimension under T-duality. So something else has to happen. But to know what else happens, you have to figure out what the T-duality does to the NS5 branes. It's actually discussed in my paper on 5 branes and knots. You could look at that.
Okay.
N equals 4 Youngles, just an R4 or S3 times S1.
Yes.
Has a dual description which appears to have 1/16 BPS black hole solutions. I wanted to know whether the supersymmetry preserved by these 1/16 BPS black holes is the same or simply related to the supersymmetry you preserve in your theory.
I'm afraid I don't know. The question was whether 1/16th. Sorry, you can't quite. Sorry. So first okay. So n equals 4 super Young-Mills has a dual description in ADS5 times S5. The question was about 1/16th BPS black holes in ADS5 times S5. So 1/16th BPS means something slightly different because you're including superconformal symmetries in the counting. So 1/16th BPS means they preserve 2 supercharges, whereas I only had 1. However, whether 1/16th BPS black holes are related in some way to the Wilson operators I was discussing is a good question. I don't know the answer. There might be something interesting along those lines.
Do I see any more hands up? No? Oh, there's one. You had another question?
Yeah. So the supersymmetries that are being preserved by the boundary condition, are they the same supersymmetries that exist inside the boundary? Because you mentioned the Wilson lines being supersymmetric in the boundary, but not.
No. There are, okay, well, I'll make a comment rather than literally restating the question. So supersymmetries square to space-time translations which act everywhere. So there aren't any supersymmetries that only act in the boundary, not everywhere. The question, I think, was how can it be that there is a Wilson operator that's only supersymmetric if it's in the boundary? The answer is simply that if you calculate the commutator with supersymmetry of the Wilson operator, you get a bunch of fields. So, well, if they're 0, then your operator is supersymmetric. But if they're only 0 with the help of the boundary conditions, then you get an operator which is only supersymmetric if it's in the boundary. That's what happens to us here.
Okay. If there are no more questions, let's thank Ed again.